Yeah. Okay. So shall we start now? Okay. Okay.
Fine with me, yes.
Okay, Professor Renner, can you hear me?
Yes, I can hear you.
All right, thank you. So I'll just say a few words of introduction, and then you can give your talk.
Yes, please.
Okay, so let's start. It's my pleasure to introduce Professor Renato Renner. He's currently a professor in the Department of Physics at ETH Zurich. He received his PhD from the Department of Computer Science at ETH Zurich, for which he was awarded the ETH Medal. Following his doctoral studies, he joined the University of Cambridge as an HP postdoctoral fellow. Professor Renner is the recipient of several prestigious awards and is internationally recognized for his contributions to quantum information science, quantum thermodynamics, and the foundations of quantum physics. He's one of the leaders in the international quantum cryptography community and frequently gives lectures on this topic to broad audiences. His research contributions are highly cited and continue to serve as one of the most influential resources for studying quantum cryptography. With this brief introduction, I would now like to warmly invite Professor Renner to give his very interesting talk on the ultimate limits of security. So, Professor Renner, please.
Okay. Thank you very much for the introduction. I hope you can hear me well.
Yes.
Okay, perfect. And I guess you can also see the screen now with the title.
Yes.
Okay, so thanks a lot for the very kind introduction. It's a pleasure to speak. I hope I just heard that there were heavy rainfalls in your area. I hope this was all okay. So I will now talk about my work on quantum cryptography. I'm actually also very much interested in the foundations of quantum theory. And you will see from my talk that these topics are actually very closely connected to each other. Questions about the foundations of quantum theory and quantum cryptography. And you will see during the talk what that means. Also, please feel free to interrupt and ask questions if that's possible technologically. I'm very happy to answer them during my talk. Okay, so let's start with one of the main tasks that cryptography, not only quantum cryptography, but cryptography as a whole wants to achieve, which is secure message transmission. And I'm sure this scenario is very well known among probably everyone who has thought about cryptography. And I'm mainly showing that just to introduce the notation and terminology and also the main characters. So the scenario that we are going to consider is the one shown here, where we have two honest parties, Alice and Bob in blue. Alice gets a message, M, and wants to transmit that message to Bob over a channel which we assume to be authentic, which means that if Alice sends a classical message through the channel, it may be overheard by an adversary, Eve, but it cannot be changed by Eve. This is a bit like actually the communication channel we are now talking over, or I'm talking here, because you can see me. So it would be very difficult, maybe it's possible with AI, but it would be very difficult for an adversary to imitate what I'm saying in such a way that it cannot be detected. But it's of course very easy for an adversary to just listen to what I'm saying here. So that's basically what one should think about when I talk about an authentic classical channel. It's a bit like a telephone line where we can hear the voice. But we also assume that we have a quantum channel available, which may be, however, completely insecure, which means that the adversary, Eve, could arbitrarily interact with the quantum channel. And so the goal is to transmit, nonetheless, a message secretly from Alice to Bob. So this would really be the scenario where I would now want to send a message to one of you in such a way that all the others don't hear it. So that's the cryptographic scenario that I will treat during my talk here. Now, I already said that, but what's the desired secrecy criterion, or what do we want to achieve? What we can achieve is that the adversary, Eve, cannot learn anything about the message. But this is not quite true, because all the cryptographic schemes we know today have the property that something is still sent over the channel. So, for example, an adversary could count how many bits are transmitted between Alice and Bob, and that gives her an upper bound on the number of message bits that are transmitted. Of course, there could be compression and so on, but it's basically an upper bound on the amount of information that Alice transmits to Bob. So it's not exactly true that the adversary can learn nothing. It's just nothing except for the maximum length of the message. And this is, by the way, in practice, sometimes already a problem, because sometimes you want to transmit messages in such a way that the adversary cannot infer the amount of communication. So what I'm now going to consider is not, so I'm not going to explain quantum cryptography in detail. Rather, I want to focus on the assumptions, mostly the physics assumptions that enter quantum cryptography. And I will do that in a way which hopefully is accessible for both those who know a lot about quantum cryptography, but also for those who know little about it or haven't yet read much about it, because I will mainly work on a toy example, basically. Okay, so what's again the main assumption entering quantum cryptography? And I mean, that's kind of the remarkable thing about quantum cryptography. It's based essentially on one big assumption, which is the correctness of quantum theory, which is, of course, something that we have verified since now exactly 100 years. Maybe you know, this whole talk is, I guess, in the framework of 100-year birthday of quantum physics. So it's certainly a safe assumption to say quantum theory is correct. Of course, there may be some small deviations, and we will talk about that later. And quantum cryptography, from that assumption, achieves that security. So it's, in a sense, a very powerful thing, or also a very remarkable thing, that only from the correctness of a physical theory we can get secret message transmission. Now let's briefly compare that to conventional cryptography. So, by the way, there seems to be some background noise. I don't know whether someone has to be muted. Okay. Okay. So, in classical cryptography, we had the situation that we needed a different assumption, namely that certain mathematical problems are hard for the adversary Eve to solve. For example, factoring large numbers. But note that the guarantee we get is at the end the same. So it's just a different assumption. So the main difference between quantum cryptography and classical cryptography is that in classical cryptography, you need to make this assumption about the hardness of certain mathematical problems, which is really something that cannot be proved, or we don't have the techniques to prove that. And in certain cases, like factoring large numbers, we even know it's wrong. So it's a slightly problematic assumption, certainly a more problematic assumption than the assumption that quantum theory is correct, which can be directly tested. Okay, so this sounds very good, but if you look, there was a lot of debate about that picture, whether this is really a fair picture, or whether some assumptions are just implicit, or maybe not, that certain claims are not even correct. And one famous proponent of this debate is Dan Bernstein. He's a very well-known classical cryptographer. And he, a few years ago, wrote this preprint on the security of quantum cryptography, where he raises concerns about the security of quantum cryptography. And I think it's a very interesting paper that Bernstein wrote because it's really, again, about the foundations of cryptography. So he asked the questions whether this picture that I've just shown is actually correct, whether we can really say that quantum cryptography, the security or the secrecy of messages follows from the laws of physics. So let me briefly show this thing again. So what he questions is really this implication that from the assumption that quantum theory is correct, we can get to the guarantee that we have secrecy. Now, as I will explain in the main part of my talk, this is still kind of introductory. What Bernstein mainly criticizes is that if you read papers on quantum cryptography, then it's never precisely stated what are the assumptions about physics, which physical laws enter the security. Is it the Schrödinger equation? Is it quantum electrodynamics? Is it even some more advanced quantum field theory? What is precisely assumed about the physical laws? Having said this, one could actually ask the same question about classical cryptography. This is not what Bernstein did, but I could ask this question. Isn't also classical cryptography based on physical laws? Because after all, any classical cryptographic scheme also is implemented in the physical world. So we don't have an abstract cryptographic scheme that is pure mathematics. Everything is at the end implemented on hardware, and the hardware is physical. So we also need to make, even for classical cryptography, some assumptions about physics. And so these assumptions must be that, for example, classical physics is correct. Otherwise, the whole Turing model and so on wouldn't work. And therefore, we could also ask the question, what precisely are these laws? And is it really justified to say, to make the usual conclusions? So basically, that's the outline of what I'm going to do. I want to explain in what sense, indeed, Bernstein has a good point. It is a priori problematic to make this conclusion. And I will then also show how this is resolved, this concern, at least in the case of quantum cryptography. So that's the plan. So as I said, please feel free to interrupt if there are any questions up to this point. I would otherwise then proceed. And I will actually proceed with something much simpler than quantum cryptography, but something that already shows the main point. And I really want to focus on that. This is the one-time pad encryption. So let me briefly tell you what one-time pad is in case someone hasn't heard that. So if you do quantum cryptography, if you want to do secure message transmission, we actually have two stages. One is this first stage, which is in faint key generation, which I will come back to later. And this is actually usually in quantum cryptography done with a quantum channel. So Alice and Bob. So I have no longer written where is Alice and Bob, but on the left there is always Alice. On the right is Bob in blue, and the red part is Eve. And these arrows are communication channels from left to right. So on the left is Alice, and she would with Bob generate a key, and the key is denoted by S. A priori, it's not clear. I mean, depending on how well this key generation works, the key that Alice gets, which is S, may not be the same as the one that Bob gets. But of course, if the key generation works well, they are identical and secret. And then the one-time pad encryption is the thing that you see in light blue here on the left and on the right. It works as follows. If Alice wants to send a message M to Bob, she adds the message M to the key. So for simplicity, you may assume that both the message and the key are just one single bit. So they add these two bits together, modulo 2, and call this the ciphertext bit. So for example, if the message is 1 and the key is 1, the ciphertext bit is 0. Then Alice sends this ciphertext bit over the classical authentic channel to Bob, which means, of course, that the adversary Eve may capture this ciphertext bit C. And Bob then does a decryption operation. He just adds again the key modulo 2 and gets back the original message. So in our example, where the ciphertext was 0 and the key bit is 1, they would add up to 1. So the deciphered message is again 1. So that's what is called one-time pad encryption. And it's called one-time pad because for every new message bit, you need a new key bit to encrypt it. Now, let me very briefly tell you why the one-time pad encryption actually works. This is just a description of what it does, but why does it work? One always has to show two separate things. One is the correctness and the other is the secrecy. The correctness is almost trivial. So the correctness just says that if the key is correct, which means that if the key that Alice uses, S, is the same as the key that Bob uses, S prime, then also the message will be correctly received. So how is this argued? One just does a calculation. One just says M prime is equal to C plus S prime, but C is by definition M plus S. So in this light blue box, you see that everything is added together, M plus S, that's what was the ciphertext, and then plus S prime. And now because we are calculating modulo 2, if S is equal to S prime, this would just be M plus 2 times S, but 2 times something modulo 2 is just 0, so it gives again M. So this already proves that Bob will receive the correct message M. So what Bob decodes, M prime is equal to the original message M that Alice entered. The less trivial part, but still a relatively simple part, is secrecy. So here one wants to show that the adversary, Eve, learns nothing about the message. What are the assumptions here? The assumption that we need to make is that the key that we get is secret. What does that mean? What is a secret key? A secret key is a key that, first of all, is uniformly distributed. So in the case that I mentioned, where we only have one single bit, the bits 0 and 1 are equally likely. But an additional crucial property is that the key S is independent of everything else. In particular, it has to be independent of the message. This is expressed by this formula here. This means that the joint probability distribution of S and M is equal to a product distribution of the key and the message. Now let's see how this implies security. So the proof is, again, very simple and shown in this light blue little box. So one calculates the probability of the ciphertext conditioned on the case where the message is 0. So what this first expression here means is how likely is it that the ciphertext is 0 if the message is 0? This, of course, happens precisely if the key is 0, but that the key is 0 is by definition or by assumption has probability 1/2. Now I can do the same calculation for the case where the message is 1. I can ask how likely is the ciphertext 0 if the message is 1? And this happens exactly if the key is 1, but this again has probability 1/2. So what we see from this calculation is that the probability of the ciphertext is the same independently of whether the message is 0 or whether the message is 1. In both cases, it's 1/2, which means that the ciphertext is independent of the key of the message. And that's precisely what secrecy means, because the adversary sees the ciphertext, but if the ciphertext is statistically independent of the message, then it, of course, provides no information about the message. So even if the adversary learns the ciphertext, the adversary, Eve, cannot infer anything about the message. So I now kind of showed that this one-time pad is secure. This is a mathematical proof. But now the big question that I want to address here is this actually sufficient? Can we conclude from that the one-time pad, when we use it, is secure? So this sounds like a stupid question because I just proved it. But of course, that was the point of Dan Bernstein. We may have ignored certain implicit assumptions about physics. So let's try to see what physics tells us about the one-time pad encryption. So let's focus just on the encryption part. This is this thing on the left that you see. This was the encryption scheme. The encryption just takes the message and the key S. I mean, by the way, the key is called S because it's a secret key, and S stands for secret. So this is the calculation that Alice has to do to encrypt. Now the point is that this calculation is actually an abstract, somehow an abstraction. We are just assuming that we can do this calculation and that the ciphertext is at the end a bit between 0 and 1. But let's now think about an actual implementation of this. And in an implementation, we will somehow have to encode the bit M, S, and C into a physical information carrier. And the physical information carrier is, for example, a voltage of a computer chip, for example. Let's just take this example. So what we want to do is to say that, for example, the cipher, in this diagram, what you see here is on this horizontal axis, you have the 4 combinations of what the values of F of M of the message and the key could be. And then you have the output voltage of the device. And 0 and 1 are encoded in different voltage values. So for example, if a message and the key are both 0, then the ciphertext should be 0. So there's a voltage here. And in these 2 cases, it has to be 1. Here it has to be 0 again. So in implementation, instead of having a binary number, C, we have actually a real number, which is either 0 or 1. But now you see the problem. This is the case if you have a perfect implementation. Now, if we actually do that in any realistic device, we will have some small fluctuations, which are just due to imperfections of the device. The point is that these imperfections, you could say this is just a practical problem and not a fundamental problem. However, the imperfections, even if they are arbitrarily small, they are still there. So the point is that you can never build a device that is absolutely perfect. You will always have maybe a difference which is as small as you like, but it will never be exactly 0. So in any realistic implementation, the device that you have has an output value, an output voltage, which may slightly depend, which may be different, for example, in the case where the message is 0 and the key is 1, from the case where the message is 1 and the key is 0, despite the fact that the logical value in both cases is a 1. And this is, of course, a problem, because if now the value C is sent over the channel and Eve captures it, Eve is not bound to just measure the binary value. She can just get the full voltage out, if you like. I mean, if you think of this as an electrical current. And for example, if she gets out that the voltage is here and she knows, I mean, she can do tomographic checks in a sense. She, for example, knows that the device here has this small imperfection. Then she can conclude from that the message must have been 1, and therefore she can learn the message. So the bottom line is that as soon as we go and take the abstract idealized scheme and realize it in practice, we run into a potential problem, because the abstract information, the 0 and 1s, are actually encoded in continuous physical values, like a voltage. And this voltage, being a real number, could be measured by the adversary, in principle to arbitrary precision, unless we make certain assumptions about the adversary. So this is a potential problem. I'm not yet saying this is actually a problem, but it's at least a potential problem that we run into. And this is the type of problem that Bernstein actually mentioned. He mentioned these problems in the context of quantum cryptography, but as I just showed, this is a problem that can arise already in classical cryptography. So we can ask, if this problem arises, if even the one-time pad, which counts as the most secure encryption scheme, has this problem, does physics allow us to keep any secrets after all? Let me briefly come back to Bernstein's worry. So what he actually pointed out in his paper that I've here again cited is the following. He said that if we do cryptography, we have usually the assumption that the honest parties, for example, Alice, is in an isolated lab. But in principle, the adversary could control the whole region around the lab. And if the isolation of, if physics may be such that a perfect isolation is not possible. So he was actually arguing that even if we shield with a Faraday cage or so Alice's lab, there is still some very small residual electrical field outside, and this field will depend on what Alice is doing inside the lab. So what Bernstein writes in his paper is that in principle, Eve could install lots of antennas here around Alice's lab. And if he completely controls the electromagnetic field around Alice's lab, Eve could in principle infer information about Alice, unless the isolation is absolutely perfect. But he then argued that it can, for fundamental reasons, for physical reasons, never be perfect. And so what Eve could see is she could measure different voltages, even in the case where Alice doesn't even communicate. So this is even a more severe problem than I mentioned before, because here Alice hasn't even communicated. She just does a local calculation in the lab. But Bernstein said, even then, there is some, there are charge carriers or some masses that you move. And then there's, for example, also a gravitational field around that you could measure. So it's impossible to keep all this information in the lab. And so Eve will get that information out. And maybe it's just a small difference in some voltage or so, but still Eve can get that. So let's analyze this in more detail. So in order to do that, I draw the same situation that you have seen here. So let me briefly go back. This situation, I've drawn that now in terms of a circuit diagram where time goes from left to right. So you see here in the blue part is Alice's lab, and the red part is again the region accessible to the adversary. Now what does Alice do? As a circuit diagram, she takes the key S, she takes the message M, she does this calculation, and then she has the ciphertext which she keeps in the lab. But let's now assume that there is a very weak, so that this implementation is not perfect. So in the sense of what I said before, there are maybe some charges that are moved in this lab, and these charges create an electrical field. An electrical field can never be shielded perfectly. They also generate the gravitational field, and the gravitational field cannot be shielded. So Eve may learn some information. Now, is this really a problem? The answer now, interestingly, depends on what physics that we are considering. And I will make three considerations. I start with classical physics, then we will look at the same thing within quantum theory, and then I wrote here quantum gravity, which we don't have yet, but you can understand this as some theory beyond quantum theory. For example, a future theory of quantum gravity. What does it tell us about the possibility to keep secrets? Now, let's start with classical physics. In classical physics, all information is encoded in real values. I mean, we know that from classical mechanics, positions and momenta of particles are real numbers. Also, the values of electrical fields are real numbers. And even the tiniest interaction, even if it's arbitrarily small but non-zero, will change these values. So this means that even if this interaction between Alice's lab and the region accessible to Eve is arbitrarily small as you like, but not zero, you will have, according to classical theory, some values which are different depending on, for example, what the message is, whether the message is 0 or 1. So this is just, actually, this is very generic. You can just choose any interaction you like, as long as it's not a trivial interaction, which means it's no interaction. You will see some effect of what's going on here. And the point is really that, according to all classical physical theories, phase space is a continuous space, and there is no discretization. So even the tiniest deviation results in a different state. So if the adversary has a precise enough measurement device, she can always recover the information. So this really means if the world was ruled by completely classical laws with a continuous phase space, then cryptography would not be possible with realistic devices because, as I said, we can never perfectly shield the lab. This is fundamentally impossible. As I mentioned, at least gravity cannot be shielded. And if you do some calculation, you will move around some energy, and the energy is a source for the gravitational field. So you will have this effect. So this is a quite drastic consequence. It says that if the world was classical, it's impossible to keep secrets. So that's a kind of devastating maybe conclusion for classical physics. So let's move on to quantum theory, because after all, the world is not ruled by classical physics. So here I've now added, I've changed the diagram a little bit. So let's now assume the world is quantum, which it is, of course, according to the best of our knowledge. And now I've modeled Alice's lab in the following way, that I have one line which encodes Alice's, like the secret key that Alice uses. This wire is the message, but now I've drawn a third wire, which is all other information that Alice has in her lab. So you can think of this as some auxiliary information that Alice has. Now she still does this calculation of C, and of course this calculation will also produce other degrees of freedom or excite other degrees of freedom in Alice's lab, so there will still be some auxiliary information in Alice's lab. There may also be some interaction again with the outside world. Now the point is the following. Let's suppose, this is just an assumption, but let's suppose that in principle there would be an action that we could carry out on Alice's lab that would completely undo this operation that Alice did. So it's this, what I called U in light blue, would be the reverse of this box that calculates C. So let's just assume such a operation exists for the moment. I will later justify it, but let's suppose it exists for the moment. Then we would, of course, the final state of all the systems. So here I've drawn a little row on the left. Rho means the initial state of the key, of the message, and all the other information, degrees of information in Alice's lab. And the rho prime, after applying this reverse unitary, would be very close to each other. This is written here. So we assume there is a unitary U such that F stands for the fidelity. The fidelity between rho and rho prime is almost 1, independently of what the initial state is. So the total thing acts like an identity. Let's suppose such a U exists. Now, this implies that if the state of Alice's lab was pure at the beginning, then if the fidelity of the final state rho prime is almost 1, then this rho prime is still almost pure. Now, there's an important property of quantum physics, which I will not prove mathematically, but everyone in quantum information or in quantum theory knows that a pure state cannot be correlated to anything else. Actually, this follows, I mean, for the experts, this follows from the Schmidt decomposition. If you have a correlated state between two systems and you write it in the Schmidt decomposition, then you will see that the states on the individual subsystems is not a pure state. So this means conversely, if the state is pure on a subsystem, then it cannot be correlated to anything else. But now, because it's not correlated, this means that in particular, this information SM and all the auxiliary information that is in Alice's lab cannot be correlated to this information that goes to the adversary. Or let's say if it's almost pure, then it's almost not correlated. And by almost, I mean by some small value epsilon. So one can now conclude that under this assumption that such a unitary exists, the probability for the adversary to recover the message is almost 0. It's bounded by an epsilon. So this is actually quite remarkable that quantum theory tells us that by having a condition which is completely testable within Alice's lab, I've still not argued why such a U exists, but it's certainly something we can do in Alice's lab. We can infer how much information has potentially leaked out. So in other words, by the sheer possibility to actually undo an operation in Alice's lab, we can conclude that no one else, in particular no adversary, can learn anything about what's going on in the lab. So that's somehow what a very particular property of quantum theory, which doesn't exist classically. Classically, whatever we can do here doesn't help us inferring what happens here. I even argued before that in a classical world, Eve can always recover the message. But here in a quantum world, because of this argument that a pure state cannot be correlated to anything else, we can conclude that there is no information leaking provided such a unitary exists. This raises the question, why should such a unitary here exist? And in general, it doesn't, because, of course, if what I just showed is that if it exists, then no information has leaked. So this means that if we here have a very bad implementation that leaks information to the adversary, then certainly such a unitary cannot exist. But now the point is that we can actually do this operation here, the calculation of C, in a way such that such a unitary exists. It's maybe a bit an expensive way to do it, but fundamentally it's possible. Namely, what we have to do is to do whatever happens here, all the calculations that Alice is doing, we do it with a fault-tolerant quantum computer. Why am I saying that? If you do an operation, I mean, this is a purely classical operation, but nonetheless, if I like, I can even use a quantum computer to do a purely classical calculation. So the calculation that has to be done is just this one, C equal M plus S. But if I like, I can buy a quantum computer and do this calculation on the quantum computer. And because a quantum computer does the calculation just by composing unitary gates, this whole green part will be a unitary from here, from the left to the right. And if this green part is a unitary, then clearly there exists an reverse unitary, which I call U here, which reverses everything so that I end up with the initial state I started. Now, of course, in reality, I will not have a perfect quantum computer, but we have, in principle, at least in the near future, we have fault-tolerant quantum computers that can make the error arbitrarily small. So then I'm still arbitrarily close here to a unitary, and then I can undo or reverse the operation here in the blue part in a way which is almost perfect up to some small value epsilon. So this means if Alice, the honest party, doesn't just do the calculation of the XOR on a classical computer, but on a quantum computer, which is, of course, as I said, very expensive. But here I'm talking about, is cryptography in principle possible? So if we do it in that way, then we know that this condition that such a unitary exists is satisfied. And then by the argument I've shown before, it shows that Eve cannot recover the message. So this is maybe a surprising fact that I'm telling you now, that even if you do classical cryptography, like a one-time pad is actually something completely classical. If we do the calculations on a quantum computer, then we are sure that nothing can leak to the adversary, and we are, even for realistic implementations, we are safe from the adversary doing that. And by a realistic implementation, I now mean one that we can do using a quantum computer, because quantum computers are realistic. So you see, there's a huge difference in quantum. If the world is quantum, we can actually reach secrecy. I've put here some references by the way, of work that I've done with my collaborators, in particular Joe Renner, who is also here at ETH Zurich, where we describe these things in more detail and more generally, for the case you're interested. So now one can be more ambitious and ask, okay, if quantum theory is so much better in terms of keeping secrets than classical theory, what happens in case quantum theory turns out not to be the ultimate theory and we replace it with something else, like some quantum gravity theory? And in order to answer that question, I will actually make a small detour and talk about the completeness of quantum theory. This is something that is not so well known, but it's actually extremely important in cryptography, because if that statement wasn't true, then it would actually be very dangerous to do cryptographic arguments with quantum theory. So what do I mean by the completeness of quantum theory? Let's look at the following experiment. So again, time goes from left to right. So on the left, we have a state preparation. So we prepare a state psi A on this wire that is called A here. And also some arbitrary other information may go here out to another guessing procedure. So this is some information that may be some information that we cannot even describe by quantum theory, something that could go beyond quantum. But here on the A system, I have just a quantum state A. Now let's suppose I measure that state, that quantum system A, and I get an outcome that I call Z. Now, this choice just means there could be different measurements I can choose. I mean, I put here some, that it has to be a projective measurement for the things to be valid that I'm going to say, but one could choose different projective measurements in principle. Now, there is a theorem that is exactly a theorem that actually we developed here in Zurich as a connection between cryptography and the foundations of quantum theory. And the theorem says the following. It says that so let's suppose we have some theory that goes beyond quantum. So this orange part could be something that uses maybe future laws of quantum gravity or so. And so it gets some information here about the state preparation that may, again, as I said before, be beyond what we can describe by quantum physics. Let's now assume that based on this additional information, one can make a guess of the outcome here, which is better than what I could guess according to quantum theory. So for example, I mean, let me just make an example in words. So suppose this state here, psi A, is just an equal superposition of 0 and 1. And this projective measurement is a measurement in the computational basis. Then the probability of guessing the outcome, I mean, the outcome will with probability 1/2 be 0 and with probability 1/2 be 1. So according to quantum theory, there is no way I can guess this output bit better than with probability 1/2 in this case. Now what the theorem tells you is that even in a future theory that goes beyond quantum, there should be no device or no way to make a guess. So this Z prime is a guess for this set, which is accurate with probability more than 1/2 in this example, unless we violate something else. And what is violated is that measurements can be chosen freely. So in other words, what the theorem says is that so let's suppose there was a theory, let's say the future theory would allow us to make better guesses. So even if something has probability 1/2, like in this example, we could make a better prediction on what happens. I mean, by the way, if you want to have a more illustrative example, you could think of something like a double slit experiment where you split the photon, or you have some particle that you split up in such a way that it goes either left or right. And then if this, for example, you do that with photons, with a half wave plate that somehow splits or you do some, you prepare it in such a way that the amplitude for the particle to go left or right is equal, then you know that you cannot predict to which direction it will go. But let's suppose now a future theory would somehow see an additional property of the particle and tell you, oh, this time it's going left or this time it's going right. Maybe not even deterministically. Maybe the additional thing tells you with 90% probability it now goes left and with 10% right. That would be a much better guessing than quantum theory. Then this guessing procedure could also be used to actually guess the choice of measurement that was done, which means that you are no longer free in choosing. So if such a theory exists, it would actually rule out the idea that if you want to choose a measurement and by freely choose a measurement, I mean you can somehow choose how to measure, or you can choose your measurement settings independently of what happened before. Like you can turn a knob on the measurement device and no one tells you how you can have to turn a knob. You can do it as you like. If there was a better guessing procedure, this would be ruled out. So it would actually deny the free choice in a sense. So this means that if you assume freedom of choice, then there's no theory or no future physical theory that can better predict things than quantum theory. This means that the analysis we did before also applies to theories that go beyond quantum theory. So in other words, what I can infer from the theorem is that if you assume that that no quantum Eve can recover M, then also no beyond quantum Eve, so this means an Eve that has some future theory available, can recover M. So everything we can say about secrecy in quantum theory generalizes to theories beyond quantum theory, provided we assume that the freedom of choice is still maintained. So that's the conclusion that we have here the same conclusion for quantum gravity as for quantum theory. So you see, we have kind of a very unfavorable situation for classical physics. We can be lucky that the world is not classical because there we couldn't keep secrets. Quantum theory allows us to use the one-time pad, and also the same is true for future theories. So notice that the one-time pad is something classical. Nonetheless, I can, of course, implement the one-time pad within the classical laws of physics, within the quantum laws of physics, and within future, maybe, theories, and I get different conclusions. So whether something is secret or not actually really depends very strongly on in which physical theory we do the analysis. And this is very important, and the point that is often ignored in cryptography. People are thinking in an abstract model of Turing machines, and they forget that all these Turing machines are at the end have to be implemented in physics. Let's now actually return to quantum cryptography. And before, when I introduced the one-time pad, I said, let's just assume we have a key, and then we do this one-time pad encryption, which is now faded out here. But now I want to focus on the quantum key distribution part for or actually just 2 slides. So basically the reason why I told you so much about the one-time pad is that the very same analysis also applies for quantum key distribution. Quantum key distribution is just something slightly more complicated, but at the end, what happens is that we have a protocol where, for example, in an entanglement-based quantum key distribution scheme, Alice and Bob use the quantum channel to distribute entanglement. And again, we have Eve who can access things in the middle. Then they use the classical channel to actually verify whether the entanglement has good quality. And for example, if Eve disturbs this communication, the quality of the entanglement will be low. And then the honest parties can stop the protocol and say, we detected an adversary, we don't produce the key. But if the verification succeeds and the quality of the entanglement is good, they locally measure the entangled state. And if it's a maximally entangled state, for example, they get a key. And by the way, in the analysis, I just use quantum theory. For example, when we say that the key is secret, the argument is usually just to say that if this entangled state between Alice and Bob has a good quality, then it also means it's very close to being a pure state. For example, it's a Bell state. And as I told you before, if a state is pure, then it cannot be correlated to anything else. So therefore, if we now measure something from this state, and get a key out, this key cannot be correlated to something that the adversary holds. Now, of course, my point is here not to do now a security proof for quantum key distribution. The main point I want to make is that everything we said about how does this now translate to actual implementations about the one-time pad equally applies to the actual quantum key distribution scheme, which means the following, that of course in classical physics we cannot really run this quantum key distribution because we need entanglement, so we cannot do the analysis in classical physics. But in quantum theory, we can actually make everything robust. So what I'm saying here is that even if you have realistic implementations, or even if we have real devices, we can do it, but actually to be sure that nothing leaks, we would have to do all the local calculations on a quantum computer. So if I go back to this slide, this verification procedure and all that would need to be carried out on quantum computers. And then for the same reason as in the one-time pad, we would be sure that nothing can leak to the adversary. But again, for the same reason as before, it's possible to generalize everything to theories beyond quantum if we assume that the future theory, whatever it is, will not force us to give up the notion of free choice. Then everything applies. So this is the only assumption that enters additionally, that we have free choice. Okay, this already brings me actually close to the end, and I have a kind of, in a sense, at least for classical cryptographers, provocative summary. If we look at, so what I told you is actually that if we do classical cryptography, then we have to be careful whether we analyze classical cryptography in a classical world where the classical laws of physics apply, or whether we analyze classical cryptography still assuming that the implementation takes place in a quantum world. The conclusion is that if we do everything in a classical world, we are really in very bad shape, because first of all, we need to make this assumption that of computational hardness. We always need to do that in classical cryptography. But then still, even if we make this assumption, we have no secrecy guarantee, because information can always leak unless we have a perfect implementation. But as I told you before, physics tells us that nothing can be shielded perfectly. And because classical physics has this continuous phase space, even the slightest leakage of information can be in principle detected by or exploited by Eve. So fundamentally, unless we introduce additional assumptions, for example, that Eve is bounded, has only inaccurate physical devices to measure quantities, or that everything, or that Eve cannot control the whole area around Alice's lab, we cannot get any secrecy guarantee. However, this is not such a big problem, because we can still do classical cryptography in a quantum world. We just assume that the implementation is done on devices that follow the laws of quantum physics, like a quantum computer, and then we can still get the secrecy guarantee. But the message of these two parts is actually every classical cryptographer has to learn quantum physics in order to make sure he can actually prove security of his schemes in the real world. Now, if we move to quantum cryptography, we are really in good shape, because we have much weaker assumptions than this computational hardness assumption, and we still get the security guarantee. So in a sense, we have this whole class, the more quantum we make things, the better it is for cryptography. So quantum theory, somewhat surprisingly, although it's kind of, I mean, you would naively, one could think the more precise a theory is, the better it describes nature, the worse it is for cryptography, because there will be more and more degrees of freedom that an adversary can use. But this didn't happen when we went from classical to quantum cryptography. Actually, quite the opposite happened. You see, as we move from left to right and make more things quantum, things get better and better for cryptography. This tells us, again, conversely, something about foundations. It tells us that actually the step from classical physics to quantum physics is a step, if I look at it from the information theoretic perspective, is actually telling us that information we thought is kind of spread over the whole world, or can easily be spread, is actually kept local and secret. So it's information spreads much less easily than it would in a classical world. And that allows us to do cryptography in the quantum world. So the step from classical to quantum is actually more than just the invention of quantum cryptography. It's the realization that physics is such that secrets can be kept fundamentally despite realistic implementations not being perfect. Okay, with that, I'm reached the end of the talk. I would like to thank for your attention. And I also wanted to point out for those who want to learn more about what I said, it's already more than 10 years ago, but the article is still relatively up to date. I wrote some more or less popular article on the topics I've covered here, but with more technical details on how we actually do cryptography together with Arthur Eckert. He's, by the way, one of the co-inventors of quantum cryptography, and you will find it if you search for this title here. Okay, thanks a lot for your attention, and I'm, of course, happy to answer questions.
Thank you very much, Professor Renner. Any questions? Yes, okay. Also, thanks for the nice talk. This is Arijit. I have a question for you. So do you consider this consider single system? Are you considering a memoryless system? And is it practical?
So the sound quality wasn't so good. Can you repeat the question again?
Can you hear me now?
Yes, now it's okay. Yes.
Okay, so this is Arijit. I'm asking that when you consider this freedom of choice assumption, are you considering a memoryless system?
Whether I'm considering a memoryless system, is that the question?
Yes. Is it practical in real scenario?
Yes. So I guess you're talking about this this part here. Is this correct?
Yes.
Yeah. So actually, yeah, this is maybe a slightly simplified setup, but indeed you can imagine that it's a bit similar, like to a Bell type experiment, because in a Bell type experiment I can also do several measurements, like I choose between two possible measurements. And if you think of the Bell experiment, one way to kind of evade the conclusion of the Bell experiment is, let's say, maybe I should have said the following. Bell's theorem is kind of a special case of this theorem here, because it says, Bell's theorem says that there cannot be a deterministic way to know the outcome here. Of course, if this was phrased a bit differently with hidden variables and so on, but basically in Bell's theorem, one would say there is no variable, which would be called a hidden variable set prime, which allows us to determine Z. Now, if you look at Bell's theorem, then in Bell's theorem enters the assumption that you can freely choose in which basis you measure the Bell state. And the assumption that is entering here is almost the same as the one entering in Bell's theorem. And so what it means is that if I do a choice, this choice can be done random, where random means that it's independent of anything that happened before. So this is maybe related to the memory. So if I do in a Bell experiment a choice, I have the same assumption. I need to make sure that the choice of the measurement basis is random, where random means that which choice I make is independent of all the previous outcomes and all the previous choices I have made. So in that sense, it should not depend on any memory, this choice. However, there could be memory in, for example, in this device here, or so in this guessing device.
So for Bell scenario, you have two systems, right? Two space-like separated systems.
Yeah, so in the Bell experiment, yes.
But here you have single system. So, so how you can, in real scenario, how can you do that? I mean, it's independent.
Okay, yeah, that's a good question. So actually, the way this is done is that we construct from, so we reduce the argument to a kind of Bell setup. So you can imagine that we first prove it actually for the Bell theorem, where instead of having this single measurement here, one would have some more complicated procedure that first, so instead of having just this measurement, in our proof, we say this measurement could be replaced by a procedure that somehow copies the information to or that, it's not a copying, but it's kind of a, in a sense, like a controlled NOT operation that creates a system. So the system A enters, and what comes out is the system A plus another system, let's call it B. And then the measurement is actually done by measuring these two things separately. So the choices actually are, if I would have a more precise drawing, are actually two different choices, which will then go to two different parts of the measurement. So the idea is really that this measurement is somehow split into two. And then we have a separate argument that tells us if there is such an implementation of the measurement which splits it into two at space-like separation, then we can, all the predictions that are valid there are also valid for any other implementation of the same measurement. I mean, the details, by the way, I mean, don't now have drawings here, but you can find them also in this paper. But maybe the short summary of the answer is we split, so that in the proof, we argue that this measurement here can be implemented as two separate measurements on space-like separations, and then we are very close to the Bell setup and can follow the arguments there.
Hello, Professor Renner, thank you for the nice talk. I'm Shivdas Roy. My question is, if you have, so Eve, when she gets, hello?
Yes, I can hear you.
Yeah, so how does,
Oh, no, I'm sorry, now the sound interrupted somehow.
am I audible now clearly?
Yes, now I can hear you again.
Yeah. Yeah. So what does the recovery process entail when you show in the figure that there is a very weak signal, let's say some leakage that Eve gets from the communication process? How does she recover the original message M from that weak signal E? So that part is not very clear to me.
Okay, so you're talking about the classical case, I guess,
I
because
think one of the slides just one or two slides before this, I think.
this
Yeah.
one, yes.
So where you mention that E goes through a recovery, box to get M, because
Yes.
depending on, because E won't know the original encryption anyway, right? So she just gets a weak signal, but how does she recover the original message M?
Yes. So
yeah.
So thanks for the question. So my understanding is you're asking how can I kind of guarantee that she gets the message M from E? So the actual argument is here. So the important thing is here I wrote a generic interaction. So what I'm assuming here in the more, let's say, this is kind of a sketch picture, but in the proof of that, I assume that there is some like among, generic means among all possible, classically possible processes that can run here. I choose one at random, and then the statement holds with probability 1. So it's not true for every, but generically in that sense. So you can now imagine I look at the space of all possible interactions that involve these two systems and some additional system E. And now I can make these interactions very weak, but even because they are generic, you can imagine because it's classical physics, it's a bit like I choose a function at random, which takes as input 2 bits and outputs a real value here on E and the outcome C and some additional information here. And I choose this function, because at the end, this output is a real number. It doesn't matter how much it deviates, but if I choose this function at random, it will always have different outputs if the values S and M are different. And now, of course, what I'm assuming is that Eve can measure arbitrarily precisely, which is a very strong assumption, because in reality, this would be like Eve would see that in a blurred way. But if you think of it abstractly, that I just have some function which maps these 2 bits to some real value, even if that real value, if I constrain it to be very close to always being the same value, the values will still be different depending on the input. So the only, let's say, assumption I make is that because Eve has control over everything, there is no other input into that function so you can think of this box as some function, which is basically generic. And because it's classical physics, it's a deterministic function.
Okay.
And so if Eve knows that function, of course, that has to be assumed as well. So there are lots of assumptions. So Eve has to be very powerful. Then she can draw that picture and then infer M.
Okay. Thank you. Thanks a lot.
I mean, by the way, I'm not saying this is really a practical attack, but that was basically the scheme that Dan Bernstein mentioned to argue that fundamentally it's not possible. I mean, cryptography is always about not what Eve can really do in practice, but what we cannot exclude that she can do. And so the point is here, we cannot exclude that she's so powerful unless we actually explicitly make an assumption that she cannot.
Thank you. Any other questions?
Sir, there is a question in the chat box. So Sandeep Mishra is asking, so the most fundamental question on which privacy of key depends is whether we have a choice of freedom. Can you elaborate?
Yes. Okay. Yes. So indeed, what I said here in this part on when we go beyond quantum theory is that the question whether something is we can better predict the value than quantum theory or better predict the value set here than what is possible by quantum theory is related to choice. Let me maybe make an extreme example. So one extreme example of a theory that is beyond quantum theory is a superdeterministic theory. According to a superdeterministic theory, everything is completely determined a priori. And now if you assume the world was superdeterministic, then of course there would be no secrecy at all, because someone who knows the initial state of the world could predict everything at any time in principle. However, as you see, the superdeterministic theory also tells us that nothing can be chosen freely, because also the choices are now superdeterministic. And so what this theorem tells us is that this is not only the case there, so there is a fundamental link between secrecy and freedom of choice. As soon as we have a theory that allows us to better predict this value, we are getting closer to this superdeterministic theory. We have the same problem as in the superdeterministic theory, and we also lose the freedom of choice. So in a sense, it's really a trade-off. You can say quantum theory is just random enough to keep, or the indeterminism in quantum theory is kind of such that it's just compatible with the idea that we can make free choices. And as soon as we try to get a theory which is more deterministic than quantum theory, which allows us to predict things that we cannot in quantum theory, then automatically we also lose the ability that choices are can be made independently. So we are moving closer to this extreme example of the superdeterministic theory. So I think thinking of the superdeterministic theory is a good example to see the extreme case of where it leads. This is really a theory where this guessing procedure would always work. You would always get the perfect value because everything is deterministic. You would here have some hidden variable on the wire coming in, and these hidden variables would allow you to tell Z, but also the hidden variables would already determine the choice, so there's no longer a freedom to choose a different measurement. I think this is kind of, the superdeterministic theory is an illustration of what this says, and the theorem can be understood as a kind of saying, this is the only option we have. We either keep quantum theory or we get more deterministic, but we also lose the freedom of choice.
Any other question?
One last question in the chat box. So, Guru Prasad is asking, quantum gravity is what you mean by going beyond quantum theory? Why gravity affects the free of choice? It is not clear to me.
Yes. So, I mean, by going beyond quantum theory, I mean that there is a theory in which quantums. Okay, I mean that's really a good question because I wasn't specific. So what I mean by that is that quantum theory is still correct in the sense that we would say all the predictions we made so far were not wrong, but maybe they were not accurate enough. So again, to make this example of the double slit experiment, quantum theory tells us both slits. I mean, if I did measure at the slit, normally I don't measure at the slit, but let's suppose I do this double slit experiment and measure through which slit does the particle go. Then quantum theory tells us it's just half-half. This is basically a prediction which is just equally, well, I could say I don't know through which slit it goes, it's just half-half. Now, if there was an extension of quantum theory, let's say there was some additional degree of freedom in the particle, which we haven't detected so far. And this could be a degree of freedom that has to do, for example, with some property of space-time. So this could be linked to gravity, but we don't yet know what it is. But let's suppose this additional degree of freedom, if we would be able to measure it, would also allow us to tell through which slit the particle goes. Then we would not say that the previous prediction was wrong, the quantum theoretic prediction was wrong. We would just say it wasn't, we ignored certain information. We were just, there were additional things around that we were not aware of, but this doesn't mean the prediction was wrong. It was just based on a lack of knowledge. And so by beyond quantum theory, I mean something that would not, any theory that would not contradict quantum theory, but allow better predictions. And we assume, because quantum theory was so well tested so far, we can assume that this is still true, at least in the regime where we do quantum cryptography, that this will still be true for a theory that includes, let's say, some gravity degrees of freedom, even if these gravity degrees of freedom are not modeled by quantum theory. This would just be like a bit hidden variable theory where we have additional variables. And if we knew these additional variables, they would allow us to make better predictions. But it doesn't tell us that the predictions we made before were wrong. They were just not very informative. And so that's the spirit in which what this theorem tries to say, that we have just some additional degrees of freedom, which in quantum gravity could be some gravitational degrees of freedom that we ignored so far, and which may be described by something that is not exactly quantum theory. But it's not that we would say quantum theory was wrong. If we found later that quantum theory was completely wrong, then everything I said would not apply, because then we would have to revise everything. But that's, of course, unlikely because quantum theory is already tested so well. So we assume that quantum theory is still kind of the correct limit based, or is at least approximately a good theory. But maybe there could be additional degrees of freedom that allows us to make predictions where quantum theory doesn't. And that's still fine.
I have a question regarding this secrecy when you consider QKD. So if you consider no signaling correlation instead of quantum, I mean, instead of the quantum correlations, will it give better secrecy in terms of secret key?
Sorry, if you consider what correlations? I didn't.
No signaling.
If you get non-signaling correlation, yeah. So that's a good. So you're saying if we do, for example, QKD and we have non-signaling correlations like a PR box or so, is that?
Yeah, PR box, yes.
Yes. Yeah, that's a very good question. So actually, it doesn't give us better secrecy in general, but it allows us to do it with simpler protocols. And the reason for that is the following: that when we look at the PR box, so the PR box is kind of a correlation which is much stronger than quantum correlation. So we think it's actually better than quantum and would give better secrecy. That's why this is a very good question. But now in the PR box, you only consider two possible measurements. So you have a bit input on Alice's side and one bit input on Bob's side. Now, if you allow the protocol to have more measurements, for example, we allow to have, let's say, if you think of measuring a qubit or a spin particle, and if you allow measuring the spin particle with respect to any arbitrary angle, then you get something like a generalization of the Bell experiment, which is called the chained Bell experiment, which is actually the basis, by the way, of this proof that appears. Let me briefly go to this paper. So the paper that is cited here with Roger Kolbeck has a description of that. So it's called the chained Bell inequality. And this chained Bell inequality has the same property as a PR box in the sense that you can always almost deterministically say if Alice has a certain outcome, what's the outcome of Bob, and vice versa. So it's a bit like in the PR box if you know the inputs. So you get rid of this randomness. And so if you use these chained Bell inequalities, you get the same, let's say, guarantees on the key as if you did it with a PR box. And this was actually used in a famous paper by Barrett, Hardy, and Kent, where they proposed non-signaling cryptography. So that's one reason why you cannot get better secrecy. The other reason is that you can always amplify things. So I've not put that here, but if you look at the quantum key distribution scheme, this would be an ideal scheme where you have maximal entanglement. And if you now would, let's say you have not perfect entanglement, you could still do things like privacy amplification and error correction to make things better. So the point is that even in the quantum case, we get actually perfect secrecy. Now you could ask, why is it then the case that let's say there is an interest in looking at PR boxes to generate keys? And so the advantage you get is that it's in a sense more self-contained. So you can say that if you do an experiment, like if you have a quantum key distribution, or if you had a cryptographic scheme that would produce the key based on PR boxes, then from just looking at the statistics of these boxes, you can conclude that the key is secure and you don't have to know anything else. If you do it with quantum correlations, you still have to do, in a sense, additional experiments that would tell you that in principle you could have measured in a different basis. So this is a bit implicit again in this theorem that I had mentioned here, that the theorem assumes that even though you didn't do certain measurements, you could have chosen these measurements, and according to quantum theory, we know that they were correct. So the bottom line of this is that if you did a cryptographic scheme on a PR box, you would not even have to assume the correctness of quantum theory, and you would get secrecy. if you believe in the correctness of quantum theory, then there is no difference in using just a normal QKD protocol. But so in a sense, one could say that using a PR box scheme, if such PR boxes existed, would give you a security guarantee without assuming quantum theory. But the same, as I said, could be achieved with these so-called chained Bell inequalities that are described in this paper. So it's not so clear whether there's really an advantage. But it's a very nice kind of research field, because people were actually studying what are the limits of how far we can go.
So I have one more question. Actually, this is not in your slide. When you have this secret key rate, there is a term smooth mean entropy. Can we actually estimate or precisely calculate that from the experimental data, or we can give some bound for that?
Yes, that's a very good question. So let me just give briefly the context of the question. So if we have here, again, this scheme, this QKD scheme, the way it's described here is if the entanglement here has a very good quality. And then if it already has a good quality, we can directly measure it. If the entanglement doesn't have a good quality, we need to amplify it in a certain sense. So we need, as I said, some procedure like privacy amplification. And in order to quantify how good the entanglement is, we need an entropy measure, and the relevant entropy measure is the smooth mean entropy. Now, there are several methods that allow us from the verification procedure to find lower bounds on the smooth mean entropy, which we need. So we cannot actually calculate it directly, but we can find a lower bound, which is good because we need to make sure it's at least a certain amount of entropy in it. And there are basically two methods that are now used very widely. One is called the entropy accumulation technique, where one actually looks at the entanglement that is that is present in each signal. So at the end, I have, of course, many signals. Alice has sent lots of photons to Bob, and I can now look at the entropy that is in each photon. And then the entropy accumulation technique tells us that the smooth mean entropy can be calculated by adding up the von Neumann entropies of the individual parts under certain independence conditions, which are kind of, in a sense, some Markov type conditions that can be argued by doing the protocol sequentially. So that's one technique. The other technique is to use the Definetti theorem, which tells us that if we symmetrize everything, so if we assume that the protocol is permutation symmetric, which means that it doesn't matter in which order I executed the rounds, then I can, the Definetti theorem tells us that the entropy, or that the relevant state of the system is a so-called IID state, almost. So it's just independent repetitions. And then I can use the so-called asymptotic equipartition theorem, which gives me, again, a bound on the mean entropy based on the von Neumann entropy on the individual signals. So the goal is always to relate the entropy of all the joint signals that were sent between Alice and Bob to the entropy of one single signal. And so this, I think I think the most efficient way is now to look into this entropy accumulation technique.
Okay, so is it for like asymptotic limit or for finite key analysis?
That's a very good question. So for a long time, people only looked at asymptotic limit, but in practice, that's completely useless because we need to know how much data we need to collect until we can make a security statement. And the entropy accumulation technique gives you actually very explicit bounds. And there were actually very recently a few very nice works by people who improved the entropy accumulation technique quite drastically. And these limits are now actually very, very tight in a sense. So if you look at the most recent works by people like, I have also one of the PhD students here, Tony Metzger, but there's also, for example, Omar Fazi and Frederic Dupuy, who are working on that and really push the limits of how well this works. And these are finite size bounds that are also extremely accurate for practical use.
Okay. Okay, thanks.
Any other questions online? Do you have any questions online? Anupam? Okay. Okay, so there's an online question by Shanu. Is imperfect implementation not unsafe in the case of classical cryptography in the quantum world?
Yeah, so if the answer is yes, if I do an implementation, what I was saying is that we can in principle do, even with not imperfect hardware, like hardware that is available today, or any hardware has some imperfection, we can reach perfect cryptography, for example, by doing things fault tolerantly on a quantum computer. But if you don't do that, then just do it plainly on a hardware which is not well protected, then it will be insecure, and that actually happens in practice. So this thing that I mentioned with the one-time pad, this problem, this can occur in practice, even in a quantum world, if this procedure here, if this calculation is not done carefully. So what I'm saying is that it's possible to do it carefully by doing it on a quantum device, but if you don't do it on a quantum device, but you are in a quantum world still, then this problem still exists. So we have to be very careful, but this is not a fundamental problem because we can correct it. So what I was kind of exploring now is it fundamentally possible to avoid this problem? And the answer is, in classical physics, it's not even fundamentally possible to avoid the problem, but in quantum physics we can. But in either case, even in the quantum case, we need to be very careful in the implementation. And this is actually the reason why there are many hacking attacks, because people are not careful exactly on this point. So that's an important thing to keep in mind indeed.
Okay, so I think any other questions? Okay, so let's then thank Professor Renner again.
Okay, thank you very much for the attention.
Thank you very
for
much
the
for your
very
time,
nice
Professor Renner.
questions.
Yeah, thank you very much for your time. So we'll end the session here. Thank you so much.
Okay, thank you. Bye. Okay, then I hope to see you another time in person. Bye, everyone.